So we saw that video, right? Explosion welding. It was almost at the end. But nonetheless, we saw the main points of those. I mean, that are relevant for explosion welding, for explaining explosion mode, right? So as you had seen there, you can either have this parallel, right? The explosive and the plate parallel to your base plate or at an angle. If it is parallel, you have this, we call it constant interface clearance gap. And if it is angular, then there is angular interface clearance gap, right? So these two types is what were highlighted there in that video. That is your detonator, your flyer metal, right? What we have seen, that is having a lower strength as compared to your base metal, right? And so as for base metal, stationary and prime component is welded to it, right? Prime or cladding metal, as we have seen, position parallel to the base component, maybe at some angle also, right? Depends, parallel or at an angle. The cladding metal, as we have seen. Explosive, it is either in granular form or and it's placed over the prime component, as we have seen. This prime component, the cladding component. The impact depends upon the type and quantity of explosive, as was explained there. The density and the type of explosive will determine the velocity of the explosion and therefore the impact. Buffer layer between explosive or the prime component to protect the surface from erosion by detonating explosive. So that buffer layer, as I said, it will cushion the effect, right, of the explosion. Standoff distance 0.5 to 1 times the thickness of the prime component, as we have seen in that video, right? Depends on the thickness. If the thickness is much less, if the thickness of the cladding metal is less, then it is taken as 0.5. The gap between the clad metal and the base metal is taken as 0.5. If it is thick, if the prime or cladding metal is thick, then the gap is equal to the thickness of the cladding metal. Detonation speed, it should be uniform and progressive. Speed of detonation front establishes the velocity at which the collision progresses. Right? The detonation speed or the velocity will determine the velocity of the collision. So you see here, as we have seen in that video, that the detonation is moving from left to right. So as it is moving from left to right, this clad metal is plastically deforming and forming a bond. That's what's happening. You see here, prime component, jet, and basically the plastic deformation is causing the fusion or welding, right? Solid state welding is right what we are calling. No melting taking place here, just plastic deformation is causing the coalescence of the two metals, right? See the process variables. The angle of the prime component and velocity depends on all these factors. What angle to keep and what velocity of detonation to keep depends on these factors. The type and amount of explosive, as we have seen earlier, that matters. Thickness of the prime component also. Mechanical properties of the prime component also, right? The cladding component. Because as I said, low strength or high strength, like that. Standoff distance employed between the two. Welding variables are your collision velocity, right? These are all factors that you can tweak to be able to achieve a better weld, right? Depending on the type of material and etc. So collision velocity is what we can, is one factor. Collision angle is one factor, and the prime component velocity is also another factor that can be changed to change the quality of the weld. Extent of waviness depends on collision conditions, but determines the bond strength, right? The waviness that you achieve, as we have seen in the diagram earlier, it depends on the collision conditions, but it determines the bond strength between, that is achieved once the weld is done. Quality of explosive weld joints. The quality of bond is determined by these tests, either it is destructive, chisel test, shear test, or tensile tests, or non-destructive tests, right? That is where destruction is not happening. So you're trying to test it when while the tested material is intact, right? So that is what a non-destructive test is. Joint quality depends upon nature of interface, the properties of metal components, strength, toughness, and ductility, right, of the metal component. The chisel test, as you can see, using a chisel, you try to separate it to test how much is the strength. No separation at the weld in this stainless steel copper specimen, right? So there is some threshold force that is applied to check the uh, strength, right? Advantages of this type of welding, it is the ability to join a wide variety of similar and dissimilar metals, right? All these things: carbon steel, stainless steel, aluminum, titanium, and steel, right? So dissimilar metals can be joined because, as you can see in the previous process, when you're trying to melt, one is having a higher melting point, the other is having, as for example, here you see, carbon steel is having a higher melting point, stainless steel is having a lower melting point, aluminum, titanium, this one is a higher melting point metal, this one is a lower one, titanium higher, steel lower. So when this combination is there, and particularly titanium, which is quite what do you call, sensitive to reactions, right, when it is subjected to high temperatures. So and the fact that you have dissimilar metals, so that is what leaves what do you call this explosive welding feasible, right? Because of the difference in the melting points, one would be melting at a higher, I'm sorry, one would melt at a lower temperature, and the other would melt at a high temperature, causing problem in joining, and the bond that will leave will also be, it will not be that sound, right? The strength reasons, for strength reasons, for reactivity reasons, we're not going for other types of welding, but we can go for this type of solid state welding process, that is explosive welding. Large size range, right? 6.5 centimeters square to 37 meters square is possible. No upper limit on the thickness of base material, right? If the base material thickness is high, then we are keeping a higher standard of distance, right? Thickness of the prime component may range from 0.25 to 30 mm, right? We are able to achieve the welding from these ranges also, thickness ranges. Limitations, it is limited to overlap joints or cladding, right? When you're trying to have overlap joint only, this is possible. As for butt joint, this is not possible, isn't it? We have seen what is a butt joint right at the very beginning of this unit, right? Wherein the two sheets or two metals are trying to join head on, right? If we are trying to see this side view or the front view, if you want to call it, right? This is your front view, and this is your front view, and this is your top view. So when the metals are facing one another, right against each other, that's called a butt joint. We have seen the types of joints, right? As I said right at the beginning of the unit, this is called a butt joint. But when they are having this overlap, one on top of the other, so that is when this type of explosive welding is feasible, but not here, right? This kind of butt welding is not possible. Lap welding is possible. So this is limited to overlap joints or cladding, right? As we have seen. Limited to flat plates, cylindrical and conical structures only, right? So complex geometries cannot be welded. That's another limitation. As for applications, parts of sufficient strength and ductility to withstand the deformation at the high velocities, right? Only with those parts which can sustain those velocities and impacts can be done. Commercial application is cladding. Pressure vessel heads can be made by explosion clad plates, right? Pressure vessel heads is one specific application. Cladding of steel forgings, nozzles, stainless steel, right? All those nozzles and turbines, etc. Even those are cladded. Heat exchangers, tube to tube or sheet, right? Tube to tube joint or tube to sheet joint. Heat exchanger fabrication. Heat exchanger is one equipment or right, an equipment in the mechanical industry that is able to achieve transfer of heat, right, from one system to another. So that is, those will have joints in them, tube to tube joint or tube to sheet joint. So that is what is done with the help of this explosive welding. Pipeline welding and build up and repair, right? All these are applications of it. Even for repair reasons, explosive welding can be used. As for a common explosive, you see, as we have seen in that video, you have RDX, right? Because that is one common explosive that we use even for uh, other reasons, right? Such as your from this mining and construction, etc. Right? So the velocities achieved, even you can see the velocities that we are able to achieve with those explosives. PETN, TNT, this is one common explosive again, able to achieve 6,600 meters per second velocity. Tetryl, lead azide, beta sheet, ammonium nitrate. Right? So as we've seen, this velocity is one factor uh, that you can go for. I mean, you can decide what type of explosive to use based on the material you are trying to weld and the quality of weld that you want. Basically, the material will decide whether it can take the strength or not, and the gap that is there. All these are factors to choose this explosive, right? So I hope this explosion welding is clear to you. If there are any doubts, you can ask. We will take the attendance. Okay, then there are no doubts. Then we will end the meeting. Thank you.